So complex numbers, who even comes up with these besides the people that work in that big gray building, right? Well, we've already learned enough about parabolas, and I've talked to you before to know that sometimes a parabola can have two solutions, but sometimes it looks like a parabola has no solutions. But we wrestle with the idea of a squared, something squared ought to have two solutions. And it's true that there are two solutions here. We just can't see them. They are in the complex number, set of complex numbers. So we have to explore these so we can finish solving quadratic equations. And it turns out that a complex number is the combination of a real part and an imaginary part. Don't get hung up on the word imaginary. It's just the opposite of real. Math people are weird. They come up with weird definitions and terms. Imaginary is simply a word that is not real, so that's what they chose to call it. Every number you've ever worked with has been a complex number. It just so happens that the real part has been 0. Just like every number you could ever imagine is always a fraction. We've gone through this many times. Is the number 4 a fraction? Sure, 4 over 1. But we should just say 4, not 4 over 1. Well, likewise, all numbers are complex. Does that mean the number 4 is a complex number? Yes. The number 4 is a complex number because it is 4 plus 0i. So if 0 times I is gone, then we just have that real part there. Well, what is this I thing? I is the square root of -1. It does not simplify. The square root of -1 doesn't simplify, just like the square root of 5 doesn't simplify, right? The square root of 5 doesn't simplify either, so the square root of 5 is simply the square root of 5. The square root of -1 is also something that doesn't simplify. The square root of -1 equals the square root of -1. But because it shows up so much in the complex numbers, the people in the big grid building decided to give it its own symbol. Kind of like we have pi gets its own symbol to keep us from writing a whole bunch of numbers down. This symbol represents this number. This symbol represents this number. Okay, so that is kind of it. So let's talk about how we can simplify these things. Let's see how we can simplify the square root of -4, which seems an impossibility, right? There is no number that you can multiply by itself to give you a -4, and it turns out that there is. 2i becomes that. Well, let me show you how it simplifies out, and then hopefully you'll be able to see that you don't need that much room later. The square root of -4 is the same as the square root of -1 times 4. And if we separate this into two separate parts, we find that we have the square root of -1 times the square root of 4. Do we already know what the square root of 4 is? Yeah, the square root of 4 is 2. Didn't we define this as I? Yes, we did, which means this just becomes 2i. This right here is the same as 2i. And I can actually show you that in a calculator. If I have the graphing calculator and I want to show you what the square root of -4 equals, it doesn't work. You get an error. But the error is non-real, which means our answer is actually going to be found in not real mode, but a plus bi mode, in complex mode. And now, if we type this thing out again, we see that the answer is 2i. So the calculators can help us out greatly. You don't have the calculator, but the simplification is not difficult. If there's a negative underneath it, then there's an I on the outside of it. If the square root of 4 is a perfect square, then you have 2, and you've got it done. As long as I've got the no, I'll come back to it. So that's why this one works. So what about b? What do you think the square root of -9 is? Well, the square root of 9 is 3, because negative, there's an I. That's it. The square root of 5 doesn't simplify. Fine. But the negative does. It's an I. the square root of 5 has to stay square root of 5, and we are done. So that's how these things work. Okay, now I want to show you this idea right here with the repeated i's. Guess what I equals? I equals I. But guess what I squared equals? -1. Is it possible to have something squared equal -1? Yes, it is. How about I cubed? We get -I. How about I to the 4th? That becomes 1. And then you start realizing that I to the 5th is the same as I to the 4th times another I. So it starts recycling around. So when I get back to I to the 5th, that's going to recycle back to I. And then I to the 6th is going to be the same as I squared, which was -1. And I to the 7th is going to be the same as I cubed. Just keep subtracting 4 away, except we start to get some trouble with the calculator. The calculator starts to get confused when you get into some higher powers. So now we've seen how the pattern works. Let me go back to this right here. So I want to tell you these things. I is I. I squared is -1. I cubed is -I. I to the 4th is 1. I to the 5th, it recycles, I. I to the 6th is -1. I to the 7th is -I. I to the 8th is 1. And it keeps repeating over and over. So what you can do is recognize that the powers of 4 just go away. So that's why I have in my notes that what you can do is take the exponent that you want, divide it by 4, the remainder is your new exponent. So 22 divided by 4 is 5, with a remainder of 2. That means I to the 22nd is the same as I squared, which is -1. I to the 153rd, what's 153 divided by 4? Looks like 1, a remainder of 1. So that means I to the 153rd is the same as I to the 1st, which is just plain I. So that's how those right there work. Okay, I think that's enough for this video. That helps you with some of it. I will come back in a second section 4.8 video to talk about the how to compute with the complex numbers. See you in a bit.